Today we are going to see types of matrices. On the screen you can see four different types: row matrix, column matrix, rectangular matrix and square matrix. These are types of matrices based on the dimensions of the matrix. Now you can see the row is 1 by n matrix, where column is m by 1 matrix. Rectangular matrix is m by n and square matrix is n by n. Okay, we will see some examples of this. Now you can see in the row matrix there are elements only in a single row. There can be different number of columns here, but only one row is there. So such type of matrix is called as a row matrix. Then we will see column matrix. Column matrix is the matrix in which there is only one column and there can be n number of matrices, n number of rows can be there. Then we have a rectangular matrix in which the number of rows and number of columns are different, and if the number of rows and number of columns is same, then for such matrix we call as a square matrix. Most of the time the matrices we use in physics are square matrices. We use the rectangular matrices very rarely. In vector algebra we have also seen we can use row matrix and column matrix as a vector in a vector space and a dual space. So you are familiar with this. So we will most of the time we will see how to deal with square matrices and the different uses of such matrices. Now we are going to see some more matrices. First one is a diagonal matrix, then scalar matrix and unit matrix or identity matrix. Now earlier four types were based on the dimensions of the matrix, but now we are going to see the types of matrix based on the contents or the elements contained in the matrix. Now the diagonal matrix is the one if the matrix has the only elements along the diagonals and all off diagonal elements are 0. Such matrix is called as a diagonal matrix. This diagonal matrix, the diagonal elements, these are the diagonal elements, they might not be same, they can be different, they can be real or imaginary, but all off diagonal elements must be equal to 0. Then only we can call such matrix as a diagonal matrix. Then we will see what is a scalar matrix. Okay, before that we can have the representation. In short, we can write diagonal of 1, 2, 3. So the diagonals in sequence 1, 2, 3. All other elements are 0. This is the representation of diagonal matrix. So scalar matrix is the matrix of which the diagonal elements are same and all other elements are 0. So this is a diagonal matrix itself, but the thing is that all diagonal elements are same. Therefore we call this as a scalar matrix. Now the unit matrix is the one. It is also a scalar matrix having all elements equal to 1 on the diagonal and all off diagonal elements are 0. Such matrix we can call as a unit matrix or identity matrix, and such matrices are shown by the English letter I, capital I, and this is a three-dimensional matrix, so I have written here I3. If in general there is a n dimensional matrix, then we write this as In. Okay, so In is a n dimensional identity matrix, or we can call as a unit matrix. Then there is one more type which is called as null matrix. Null is representing 0. So if there is some matrix in which all the elements are 0, then such matrix is called as a null matrix. Then we can see there are more types. We have triangular matrix, and the triangular matrices are again divided into upper triangular and lower triangular matrices. In the upper triangular matrix, all the elements below the diagonal are 0, and the elements above the diagonal may not be 0. Some elements may be 0, but if all the elements below this diagonal are 0, then we call such matrix as a upper triangular, because all non-zero elements are in the upper side of the diagonal. Therefore, we call this as a upper triangular matrix. Similarly, the lower triangular matrix has the diagonal, and above that diagonal all elements are 0. Okay, and all the non-zero elements are in the lower side of the triangle or of the diagonal of that matrix. So such kind of matrix is called as a lower triangular matrix. Now, based on symmetry, we have two types: symmetric matrix and skew-symmetric matrix. In a symmetric matrix, we have the diagonal elements, and if I have this element, then I will have the same element on the other side. Similarly, you can see this element and this element is same, and these two elements are same. So this is a symmetric matrix. So if you see along the diagonal, and if you take a mirror image of this matrix, then both images are same. Such matrix is called as a symmetric matrix. If I have to write the equation of this, then I can write Aij is equal to Aji. This means the element Aij must be equal to Aji. So this is one element, this is 1 2 1 3 2 1 2 2 2 3 3 1 3 2 and 3 3. So you can see element 1 2 and element 2 1 are same. Element 3 1 3 and 3 1 are same. Element 2 3 and 3 2 are same. So if I change the values of Ij, then we will get different elements. But this symmetric matrix satisfies the condition that Aij is equal to small aji. So if I am writing small letters, this means we are writing the elements of the matrix, and if we are writing capital letters, then this means we are writing about the matrix. Okay, before seeing that matrix element, we will see one example of skew-symmetric matrix. Now you can see here the diagonal elements are 0, and you can see here Aji is negative of Aij. You can see here also it is negative of this. -1 is here is 1. So from this we can write that Aij is equal to minus of Aji, and this is the condition for skew-symmetric matrix. And to satisfy this condition, diagonal element must be equal to 0, because A11 is minus A11, and any element, if it satisfy A is equal to minus A, then that element has to equal to 0. Any other number cannot satisfy this property, and therefore all the numbers on the diagonal of skew-symmetric matrix is always 0. We have two more types, Hermitian matrix and skew-hermitian matrix. The difference between symmetric and Hermitian is that in symmetric matrix we only had real numbers. Here we can have imaginary numbers. So I am writing here 1 minus I is a complex number, and 3i is also complex number. Okay. So you can see the complex conjugate of this number is given here. As this is a real number, we have the same number on this both positions, but here you can see here is 1 minus I, here it is 1 plus I. So the sign of complex part is being changed. Here also you can see here it is 3i, here it is minus 3i. So the sign of this part is changed, and on the diagonal there are real elements. Okay, there are real numbers. Now if we see the skew-hermitian, okay, we will write the condition first. So this means Aij is equal to Aji conjugate. Now for the skew-symmetric matrix, what we have is all the diagonal elements are either 0 or pure imaginary, and this satisfies the condition Aij is equal to minus Aji star. Now you can see here on the diagonal there are only imaginary numbers, pure imaginary numbers are 0. So to satisfy this condition, we have this condition like we had in skew-symmetric matrix. We can only have zeros, But here we can also have some pure imaginary numbers. You can see the real part has opposite sign. Here also real part has opposite sign, but the imaginary part it has same sign. You can see here 2i, 2i. Here I, here it is plus I. Real parts you can see 3 become minus 3, 2 become minus 2. So this is called as a skew-hermitian matrix.